Okay, so let's start. First, why I picked this topic. So I used to work for a long time at a company called Tieto Every. So I was working on payment card software that is processing your payment card transactions. I did a lot of things there. So one of those things was that I developed an accounting system that, so in C++ and SQL, and that was handling hundreds and thousands of business transactions per second. So in these, so we did the official benchmarks. We went more than 5,000 per second, real card transactions, and only a smart part of that was this accounting system. And we did this all with a regular database. So it was Oracle, but I mean, it's still a general purpose database. So we didn't have to use any key value stores. We didn't have to use NoSQL, like web scale databases or specialized databases like Tiger Beetle DB. So of course, there were unsuccessful approaches to this problem, but finally we refined it and we found what works. And so I know a thing or two about database concurrency. So now I work in a completely different company with which is doing which is fintech, and it's doing most of the code in Python, which is really nice thing for fintechs because most of fintechs use Java or some exotic languages, and we are using ORM primarily. So I have used SQL for most of my life, and now I'm trying to achieve things I was doing in SQL using ORM, and so that's why we have this talk. So let's first start with a simple account transfer. So what it does, it checks if the account has sufficient balance. Then it debits the account. It means that it reduces the account balance. And then it credits another account, so increases balance by the same amount. So of course, in practice, the code is more complicated. So my only reason for going this simple was to fit this code on the slide. So this is Python code. If this popped up in the code review, so I might have some complaints, but I mean, mostly it looks fine. However, if somewhere in our code we are using threads, so I have to start thinking about other factors for this function. So I see that this from account and to account come from the outside. It means that those could be modified by some other threads, and I must take care of concurrency issues. So where are those concurrency issues? So there is a race condition. So it's a classical time of check to time to use. So we check the balance that is sufficient to withdraw the amount, and only later we decrease the balance. And between those two steps, some other thread might do the same. And as a result, the account would go into negative balance. So this is a thing that we want to avoid. Another thing that is not so visible, there is also a possibility of lost updates on those lines that decrement or increment the balance. And you might ask, why is it so? Well, it turns out that in Python, those lines are actually not atomic operations. If you go into the bytecode, so bytecode has two parts. So in one bytecode, it loads the current value of balance, then it does the increment of the balance, and then it stores it back. So in between reading and writing the balance, some other thread, again, might do the same, and so we lose an update to this account balance. So how do we solve this? So this is something called shared memory concurrency. So the idea is that there are multiple threads, and all of them try to access and modify the same memory. And if you Google for the how to do multi-threading programming, and you will come up with a lot of search results. You will find about mutexes. Maybe you will find about fast user space mutexes. Then you have read-write locks, spin locks, latches typically in the database, then semaphores, which is a classical topic. Then you might find data structures that are meant only for single-threaded programs. Then there are data structures that are thread-safe, and then there are data structures that are thread-safe, and also they are lock-free, so they don't use any locking at all. Then there are atomic operations and kind of more complicated atomic operations like compare and swap, and approaches like read, copy, update. And finally, we have like approaches how to structure the program by using actors and not sharing memory at all. So there are a lot of topics. Of course, since we are in Python, and Python is so bad at multi-threading, we usually forgot about a lot of these kind of topics. But even Python has locks, so how to fix the code using locks. So we simply add a lock to each account, and then we ensure that both of these accounts are locked, and then this code is safe. Of course, we have to ensure that nobody else, no other function ever modifies the account balance without using a lock, and we also have to ensure that there's a specific order in which we acquire those locks so that we don't run into deadlocks. But so this can be all solved, and kind of this is a safe code. But yeah, so most of the code isn't like that. So most applications have kind of this generic architecture. So we have several front ends. Those might be browser instances talking to several backend instances. And finally, they all talk to the database that is shared between them. And so for some reason, when we start writing database code, even using Django, we forget about the all locking at all. So kind of we read these accounts from the database, we perform the checks, we perform the updates, we store the result, and then kind of we treat the database as a black box, and we somehow silently hope that it will work it out fine and no problems will happen. But it's, of course, it's not true. So, and in practice, so it might be that in 95% of cases you don't experience any problems, but when you experience those problems, they are typically really hard and might even bring your company down. There's one case that is kind of publicly available, but of course, a lot of companies have this issue, but just they don't go public with it. So there was a Bitcoin exchange that basically didn't do locking between time of check to time to use, and so the balance was kind of the available amount was overspent, and they went bankrupt due to this. So how do we solve this? So there's I call this shared database concurrency, just to kind of share memory concurrency to shared database concurrency. So we have the same situation that we have several programs that all communicate with each other, but this time they do it through a database that is shared. And just to make things worse, so those programs are not actually using the data itself. So the record itself lives in the database, and what programs have is a kind of copy of that record that somehow is linked to the database. And what we try to do, we kind of try to refresh it, and then we try to store the updates and hope that this will lead to consistency. So if you try to find out how can you fix these concurrency issues, you can usually find pessimistic locking and optimistic locking. So those are the two major things. So just two topics about database concurrency and like two options what you can do. Of course, there are some resources that say, well, just use Redis for locking. And this is approach where a lot of people are not sure how the database works. And like, just to be sure, let's do another lock in the Redis database, and that should solve our issue. But here I want to look into those pessimistic locking and optimistic locking just to show how this can be solved from the database point of view. So how to solve it in the database? Let's start with the pessimistic locking. So there are two important things. So first you have to start an atomic transaction. So instead of going into this auto commit mode, you start a transaction that contains multiple operations, and then you have to do select for update. So you log the record in the database, and then you, using the same operation, you also retrieve the current state from the database. So this doesn't look so good in this kind of with the function signature that we have. So preferably, it would be better if you loaded those database objects just once, but let's just go with it so that you refresh the values from the database and acquire logs. Then you perform all the checks and then you save it. So this is kind of what we did in the Python code, so by using logs. So, but somehow the pessimistic locking, the word pessimistic sounds bad to me. So it implies that something bad is happening. So optimistic locking, on the other hand, sounds much more, much better. So what is optimistic locking? So the essence of optimistic locking is that it ensures that the row in the database hasn't been changed since we last read it. So how do they achieve it is that typically models have a new field called version, so which might be a number, or it might be a timestamp, like the last timestamp when the object was changed. I've seen implementations that calculate a checksum of all the fields, which is also okay. And then, so yes, so this version is used to ensure that the row hasn't been changed. And then important part of it is that it does retries. So it might be that some process already changed the row. So we have to retry until our update succeeds. And then there's this strange situation in Django. So if you are used to programming in Java, then this popular Hibernate project, it actually has optimistic locking built in. You just say that this field is a version field, and then Hibernate does everything for you. In case of Django, you have to install some kind of package or build something on your own. So there are three popular packages that do optimistic locking in a different ways, as I will show further. And what bothers me a bit is that some of them claim that they avoid database level locking. So keep that in mind. I will address it later. So how to do optimistic locking? So this is one of approaches by using select for update. So this is pretty much similar to the pessimistic locking, but there are kind of main differences. Is that number one, we can do the check of balance while we are not kind of locking the row. And once everything is good, just before updating the record, we do the following. So we lock a database record for the same primary key and for the version of data that we currently possess in memory. And if this lock succeeds, that means that nobody has changed the row, and we can proceed with updating the record. And during all updates, we have to also increment the version number, which is not so nice thing, because all places where you update the model, you have to remember that you have to increment this version number. Of course, the packages that you can download, those kind of can solve this for you. Then the second approach is kind of doing optimistic locking using update. And so this approach is a bit more interesting because you don't have to work with models at all. So what you need is the primary key and the version number. And so what you do is that you filter accounts using this primary key and version. So if this record hasn't been modified in the database, you get the record. So it's one. And then you do the update itself. So you decrement the balance and you increase the version number. So the downside, of course, is that since you are not using models, then Django signals do not work. And if you have some auditing packages that rely on those Django signals, then you won't see those modifications. So, but does it really avoid the database locking? So we can quickly fire up Django shell we set the auto commit to false, and we try to do this update, just as in the previous example. So it succeeds in the first session. When we try to do it in the second session, so what we get is that this update is actually blocked. So it doesn't return any result. It actually is hanging there. And it's hanging there until I perform the commit in the first session. So it means that actually some kind of lock is happening there. And we were blocked by waiting on the row. So the point is, database is always doing some locking, and that's a good thing, because database should ensure that the records are consistent. And instead of like optimistic and pessimistic locking, I like to think about it like explicit locking and implicit locking. So for explicit locking, when I request the locking, there's this our select for update that will block and wait for locks to be released. There are some other approaches, so I will not go into this because of lack of time. But so there's actually implicit locking that is happening as well. So every update will place a lock inside the database. Every delete will place a lock in the database. Even the creation of records will place a lock, and sometimes these create operations and then kind of save with force equals insert might block when you are about to violate the unique constraint. And at least for the Oracle database, there are some extreme conditions when even query set, kind of like a select, might be blocked in some specific scenarios. So blocking is happening all the time. And what I want to show is that there's a blocking on create. So you can create an account with unique key 42. Then you try to do the same from other session, and it's stuck there. It's waiting for a lock. And if you commit, you get an error in the second session, which is fine. If you do the rollback in the first session, then the second session succeeds. So that's an interesting thing. So locking and blocking is happening all the time. On each operation in database is doing some locking. And it's not possible to avoid locks when you are working with the database. And this often leads to performance issues where you see that you are trying to go as fast as you can, but your database isn't consuming the full CPU or disks fully. Your application isn't 100% loaded. The network is not busy, but somehow the application is really slow. And the typical reason for that is that you experience some locking and blocking issues in the database, and it takes typically a DBA to show you where it's happening. So, but how to avoid this? So we know from a kind of Python programming language and programming in general that to improve concurrency, you have to increase log granularity. So you shouldn't have a one global interpreter lock. Instead, you should have multiple smaller locks so that multiple threads can proceed with work without waiting on the lock. So in the database, you typically get a lock on a row if you have a normal database. And well, sometimes you can break down your model to create separate models just to get more rows and to kind of increase the granularity of locks. And then the other tip for improving concurrency is holding locks for as short duration as possible. That's clear in the programming language, but what to do in case of database. So when are the locks released in the database? This is actually from Oracle database because it has this nice phrase. So it says that raw locks are held until the transaction either commits or rolls back. So we acquire logs by each update operation, and we release them only when we commit. And the other nice thing here is that it lists that these specific raw locks, TX locks, are taken by insert, update, delete, merge, and select for update. So there is no difference at the database level for these locks. They are all the same. They are all similar locks. So the idea is to reduce the time between updates and updates that take the locks and between commit. How to do that? So I like this example because it kind of breaks your logic as a programmer. So first we debit account, then we credit it, and then we write an entry that we actually did the operation. And the first update already takes a lock, and those are released when this transaction block ends. So how can we improve it? Since we are working with databases, we actually can move those creation of objects up. So by that, we reduce the time that is spent holding the locks, and still from the outside observer, the result will be the same. So either there are all of these records, or the transaction is rolled back, so it won't see journal entry without seeing the actual updates on the accounts. So there are many ways how to do it. So the idea is to move all the operations outside the critical path. And one thing to remember is that even if you have kind of rows that look the same, not all of them are equal. Some of them might represent your account, which might get like 10 updates per day. And then there are bank accounts which get million updates per day. So then what I would do is then try to update the bank account last, because more transactions are waiting on those specific logs than on my personal account. And then one more last thing. So there's this, how this version number is incremented. So I showed you this approach, which roughly in my mind translates to this SQL, and you can see this SQL also if you look at the Django executed SQL statements. However, when I was taught optimistic locking at the database level, we typically did something like that. So we took version and we assigned it value version equals +1, which is roughly something like this, like f expression in Django. But now the question is, how does it work? Because we have several steps. So we first have to read the version number, then we have to increment it, and then we have store back. How do we not run into lost update issues? And so we have this code. It could be running from thousands of threads in parallel, and the result would be still the same. So the key to this is how the update works. So first, it filters the rows according to where clause. Then it locks all of the rows, and only then it evaluates this set clause. So it reads the current version number only when it's already holding the lock. So in Python code, this is roughly equivalent to this code. So we hold the lock while we increment it. And so with that in mind, that we kind of, if we do not care about the order of operations, how those are applied, and because this variable is always locked, then we can do simple addition and even adding negative numbers to achieve subtraction. We can do that all without explicitly locking the rows. So that could be, we can count clicks or likes and so on, or retweets, and it's also the same for account balances. So all those individual operations, if we use the current value stored in the database, those will be correct. So how to do transfer without optimistic or pessimistic locking and still have a correct result? So we do something similar to optimistic locking, but the condition for there is not on the version, but we select account if it has sufficient balance. If it doesn't have the number of rows updated will be 0, and we will raise an exception. If the account has sufficient balance, we reduce the balance by the amount, and we are good to go. And for the account where we just credit, where we increment the amount, we do not have to check it at all. We can just increment it, and it will be completely fine at the database level and completely correct. So, main takeaways. So remember that database always locks rows, and it might lead to blocking. So, and if you keep that in mind, and instead of treating database like a black box, you think that, oh, I'm doing update here, it will take a lock, and someone else will be waiting for the lock, for that lock, so I must release it as soon as possible. You will get a more performant code. And yeah, the other thing, kind of, if you start thinking about locking in the database, oftentimes you can avoid using Redis, which is kind of a common pattern. And Redis has other uses, but I mean, for locking, maybe it's safer just to stay with the database. So that's all. My own time.
Thank you so much. Yeah, perfect in time. Thank you so much. We already have one question from Slido. If you have more, please write on a Slido. And how do you test that everything works in the different approaches? There is approach to test with PyTest or unit test.
Well, no. So I haven't done that in Python. So my experience was when I was doing like C++ and SQL. So we were running specially designed concurrent tests. So we had programs that were incrementing. So if we launched, let's say, 100 processes that each increments it by 1,000,000, we know that the end result should be like that. And also, since we write those journal entries for each account, so we can compare the end balance of the account to the entries that are actually inserted in the journal. So that's typical accounting trick.
Okay, thank you. Cool. Any more question?
Thank you for talk. It's great. Can I found hidden thread to block database if I use manually transaction stop and after that transaction commit? Can I probably, if code breaks in this moment, it can be causa to block row in database? Can it be?
And what happens to the process itself? It crashes? Or?
Yeah, it's crashed.
Yeah, so typically in that case, the database session will be rolled back. So there might be session timeouts. So database will clean it up. Yeah, sometimes it might be that if you crash in the process and database doesn't know that your process has crashed, it might wait for some time. So that's typically we set a couple of seconds like transaction. It's session timeout. So once we start the transaction, it gets a couple of seconds to complete. But yeah, it happens that rows might be blocked. So what we were using also two-phase commit. And in those cases, yeah, it was typical that processes were blocked for a long time. And sometimes a DBA had to come in and remove a couple of records just to proceed.
Thank you so much. Big round of applause again.